So we are at 3 o'clock Eastern Daylight, and we are admitting people as they come in. Again, sorry for the logistics issue, just that's what we're required to do at USDA. And, we're having one issue with a joining problem. It's luckily the only one we've seen, which is, I suppose, good for everyone except for Yulong Shah, who can't get in. So we will keep admitting, and we will start our next session. And again, to remind everyone, we have the, let me get the link for the, we have a Jamboard for folks who want to post some ideas to questions being asked. There's 4 pages of questions, and feel free to have a little time there. Some of them are getting, we're getting some activity there on what's a challenge you face in your everyday soil industry research, funding, short records, finding documentation for models. What are the next big things in soil moisture science? Assimilating in situ and other types of data together, integrating discrete measurements. And then in the year 2051, what does soil moisture monitoring look like? You know, seamlessly integrated data from all sources, moisture data utilized at all scales of management. Interesting and useful data for everyone to use. I'm really trying to think of, you know, what are the scales and the latencies, and some of those kind of interesting questions to be asked. Our next section is still on in situ sensors and sensing networks, and our first speaker is Li Xu from CPC, Climate Prediction Center, if I got my acronyms right. And we will be, he will, I saw you, Lee, will be in the chat as well, and we'll be playing the video. So hopefully I will be able to make this work. Let me try one more time. Here we go.
Good afternoon, everyone. My name is Li Xu from the CPC. My presentation is title is Soil Moisture Analysis and Simulation from the National Water Model version 2.0, application for the US drought monitoring. This project is OAR service level agreement project. The name is application of National Water Model for the drought monitoring. It's during 2017 to 2020. This is a multi-center project including OWP, CPC, and the PSL. The CPC part is led by the PI is David DeWitt, and technical lead is Kingsley Mo and Hailan Wang. Also, the major staff including Mutu, Chilia, and me. The monthly technical connection is organized by the Mimi Hu at the PSL. The goal of this project is to evaluate soil moisture anomalies calculated from the National Water Model retrospective simulation in the analysis and simulation cycle to develop a prototype drought monitoring product based on this anomaly. The product will be shared with the drought monitoring authors and the drought outlook forecasters. Brief outlines. First, we will briefly introduce the National Water Model 2.0, and the second, we will introduce the soil moisture analysis and simulation cycle at the National Water Model, and also soil moisture percentile calculation based on the retrospective simulation from National Water Model, and then we evaluate the performance diagram against the USDM or US drought monitoring from the recent 20 years, And the last one is conclusion. National Water Model 2.0 is a consistent, it's a operational hydraulic modeling framework based on the WRF Hydro, simulate and forecast how water moves through U.S. rivers and streams, produce hydrology guidance at very fine spatial and temporal resolution, and complement the National Water Regional Forecast Center hydraulic guidance. Its output is hourly to 200-meter resolution stream flow and 1 kilometer soil moisture output and over 2.7 million river reach in over the corners. The forecast variable including stream flow, surface runoff, soil moisture, evaporation, snow, and other parameters. The National Water Model 2.0 retrospect simulation during 1993 to 2018 are available to compare with analysis to obtain real-time drought anomalies. The NWM 2.0 forecasts are real-time only. There are no handcasts available right now. The land component of National Water Model is non-MP. The resolution is 1 kilometer, 4-layer soil moisture. The model physics including 4 land surface physics, including water balance at bare soil, vegetation, and canopy, and 4 energy balance, including 1 complete snow model and a lake model and per moment forest modeling. The retrospective simulation is forcing by the NRDAS-2 meteorology forcing, downscaled and regraded to the 1 kilometer NWM grid. The time range is including 26 years handcast. Is currently available on Amazon Web Service via NOAA Big Data project. We analyze the volume soil moisture at 1 kilometer national water grid, and to reduce the data storage, we spatial and temporal average the soil moisture to daily mean and to the 1/8 degree with the same as NRDAS resolution over corners. The soil moisture percentile, we use a very similar method to as NRDAS to calculate the soil moisture. You use 5-day nearby soil moisture data to concatenate a long time series for the experiment PDF. With analysis of the total column of the top 2 meter soil moisture and also top soil is up 40 centimeter soil moisture. This slide shows the soil moisture evaluation against the in situ observation soil moisture evaluation from the SCAN network and the USCI network. We can see this figure from the PSL Daryl Jackson. We can see for the soil moisture less than 20 percentile at the top level 10 to 40 centimeter, the critical success index is between 20% to 40% at most locations across the U.S., with a lower value in the desert southwest and a higher value at the east and scattered location. To further evaluate against the U.S. drought monitoring, we first rasterize USDM to the regular latitude grid, and then we further separate the U.S. drought monitor to the long-term drought and short-term drought. By the definition, the long-term drought is defined by the drought persisting longer than 6 months in the past 26 weeks, and the short-term drought is the remainder just less than 6 months. This figure shows the drought area covered over corners monitoring by the USDM in the top panel and by the National Water Model in the bottom panel. The top panel shows the D0, D1, D2, D3, D4 drought in the over the recent 20 years, And the bottom banner shows the recent 18 years, 18 years national water model soil moisture below 30 percentile, 20 percentile, 10 percentile, and 5 percentile, and 2 percentile corresponding to the D0 to D4 drought. We can see from national water model slightly underestimated D3, D4 air compared to USDM. And in the overall, it's slightly underestimated the drought area. But we can see very clearly the 2012 the Great Plains drought. It's over 80% of the area in the drought, but we can see most being catch the national water model. And also 2002 the western drought were very clearly catched by the national water model. 2007 the southeast drought, and the 2011 Texas drought, and the 2013 to the 2017 the California drought. All can be captured by the national water model. This slide shows a performance diagram of national water model soil moisture percentile against USDM by the D0 and above drought. This is summarized multiple score. First is the this is the vertical axis is by the probability of detection. It's measure how much the national water model can correct detect the drought, and horizontal axis is the success ratio, which equal to 1 minus the false alarm ratio. It shows how much correct ratio of the national water model indicates drought, corresponding the USDM also indicates drought. And the count color is a critical success index, show as this color map, and the dashed line is indicate bias, which means the total ratio, how much drought can indicate by the USDM national water model compared with USDM, and each color dot is for the each week during 19 years evaluation period for the over during 2000 to 2019. So we can show the national water model do a relative moderate successful over the corners, and in the most weak is below 1, bias is below 1, which indicates the national water model will under-detect the drought over the corners. And the highest success ratio is occupied in this yellow color. This is going to match the 2012 Great Plains drought. And this indicates the national water model could be used as do the object drought monitoring. Further evaluate against by the hard to regional by region. We can see this from the total 18 region over the corners. We can see in most high score located in the upper Mississippi, lower Mississippi, and Missouri Red Ring region in the central of United States. And in the east United States, it's relatively good, but the post evaluation is located in the west region, in particular the Pacific Northwest, California, and Lower Colorado and Great Basins have lowest probability of detection. Also, we evaluate the national water model against the LDAS model in symbol as a benchmark for the soil moisture anomaly by the different drought category. This panel shows the drought predictable detected POD over the corners by the different drought category. We can say for the D0 drought, it's two model very closely. But in the D3, D4 drought category, the national water model shows slightly improved over NRDAS. Very similar in the critical success index. In the D0, D1, almost same, but D3, D4, NRDAS national water model show better result than the NRDAS. And similar the high key skill score and also the bias over corners. We can show this all the NRDAS and the national water models detect the drought over happening corners, but national water model will better detect the drought than the NRDAS2. Also, we found the national water model have some advantage to detect the flash drought, the quick intensity and the onset of drought. This is example. 2019 southeast flash drought happened in the east part of the United States. We avoid over the soil moisture percentile over this region. We can the top panel is based on the USDM drought monitoring, and the bottom panel is called responding soil moisture percentile detected by the national water model. We can see national water model can well capture this quick intensified drought events over the southeast region. Slightly overestimate the drought category, but this is a very good example for the flash drought monitoring by the national water model. During this project, we found two outstanding issues for the current drought monitoring based on the national water model. First is the relative short retrospective period. It's only 26 years. It's relatively short for the drought monitoring. Due to the short period, we need to do some special treatment to estimate the CDF than to estimate of soil moisture percentile. And the second is the mismatch between the precipitation forcing between the retrospective and the real-time simulation. For the retrospective, the meteorology forcing is from the NRDAS2 is consistent, but for the real-time national water model forcing, precipitation comes from the HRR, RAP, and the MRS blending the meteorology forcing. Let's make some difference. We need to consider in the future application for the drought monitoring. This slide shows we do some comparison between forcing. Left shows the NRDAS forcing for the meteorological, and the right is for the real-time national water model forcing. Although the climatology say pretty much each other, but we still can see some difference at the precipitation distribution. And if we compare to the difference and minus by the NRDAS forcing, we can see over west region still have pretty large difference. Across much of US, the national water model analysis and simulation is relatively wider than the retrospective forcing. And over west region still have shown pretty large difference. This is where the precipitation is last constrained by the radar. So this mismatch in the operation and the retrospective forcing is a major concern, and the potential way to elevate this impact is still being explored by CPC. So in conclusion, the key results, during this project, CPC evaluated national water version 2.0 using in situ observation from the retrospective period 26 years. And for soil moisture show positive bias or the most common location, and for the drought events below 10 percentile, it's relative compared to the NLDAS land surface model, slightly better than LDAS soil model. And the national model will underestimate the drought occur in the West US and East US compared to the USDM. And current National Water Center has implemented a set of demonstration map that can be used for as a result of this project. And this map has been delivered to the NOAA field office and select partner. The mainly concern is the mismatch between the operation and the retrospective forcing. That's still a major concern, and in the future we need to elevate this impact in the future. Thank you. That's all.
Thank you, Li Shu. And Li Shu is in the chat. If anybody needs to ask a question, the National Water Model is a major initiative within the federal government. So there is a lot of energy being put there. And once it becomes online, it'll be, with a soil moisture component, it'll be a big step forward for a lot of folks with the computing power behind it. Do we have any questions for Lee?
This is Stephen. Have there been similar comparisons done between the national water model and in situ or remote sensing data sets? So the comparison with NLDES too is really interesting. And I wonder if there was something similar done with other sources of soil moisture.
Lee, if you'd,
No, I think we only focus on the national water model, so we don't do any other for the LDAS2 data.
Okay. We'll we're a little bit behind, so we'll move questions to the chat, and we'll move on to our next presentation. And Brianna Wyatt at Texas A&M will present, and she is in the chat, I thought. Wyatt Brianna in the alphabetically. So let me see if I can make this one work faster than last time.
Good afternoon. My name is Brianna Wyatt, and I'm an assistant professor in the Soil and Crop Sciences Department at Texas A&M University. Today I'm going to be presenting the results of a project we recently completed regarding testing a novel cosmic ray neutron detector in a field with highly variable soil texture. But before I start, I want to acknowledge my co-authors, Cade Flynn and Kevin McInnes, and in particular I want to acknowledge Cade. So Cade is the one who really led this study and who did the majority of the work. So the things that I'm showing today are really Cade's work. Many of you are likely aware of neutron detectors and their use in estimating field scale soil moisture. On the right hand side here we have a diagram that shows the sensing radius and typical sensing depth for one of these detectors. So these neutron detectors are able to effectively bridge the gap in spatial scale between point measurements or estimates of soil moisture and remote sensing measurements of soil moisture. They're also able to provide continuous measurements in time. Some of the drawbacks, though, are that interpreting and applying the soil moisture data from these detectors can be somewhat tricky because the measurement radius and depth vary depending on the amount of hydrogen in the environment. Probably the larger drawback, though, is the fact that these types of detectors are currently quite expensive, and their use is really cost prohibitive outside of the realm of research. So in this study, we compared two types of neutron detectors. The first is a helium-3 neutron detector from Hydro Innova. So this is a commercially available detector. These are the more expensive types of detectors. So these cost upwards of $15,000 per sensor. So on the left-hand side, we have a picture of Cade installing one of these detectors at our field site. And then the goal of our project was to compare a new type of neutron detector with these Hydro Innova detectors. So these new detectors are from Radiation Detection Technologies, which is a startup out of Kansas State University. And these detectors use an enriched lithium foil, which is a byproduct of the production of lithium-ion batteries. And because of the abundance of lithium-ion batteries and the strong production of these batteries, lithium foil is quite a bit less expensive to use than helium-3. So these lithium foil modules only cost about $2,500, though you do need multiple modules to create a single sensor. So for those of you that have never seen one of these lithium foil detectors before, I thought I'd include a photo. So on the left side, we have a picture of the inside of one of these detectors. So we have here 3 lithium foil modules. Those are the silver rectangles that you see there. And they're inside a high-density polyethylene case. On the right-hand side, you can see what the unit looks like installed in the field. So I said each of these modules is about $2,500. So that means this unit costs approximately $7,500, which, while that's not cheap, it's still less than half of what one of the helium-3 detectors costs. So it's a pretty significant cost savings. So the location of this study is in Southeast Texas at the Texas A&M Beef Center. So you can see in sub-figure B here, we have the lithium foil detector and the helium-3 detector installed at the site. We also had an all-in-one weather station, as well as subsoil moisture sensors installed at 5, 10, and 20 centimeters below the surface. However, possibly the most interesting thing about this site is the high variability of soil texture that we see in a relatively small area. So on the right-hand side here, you can see the location of the neutron detectors as indicated by the yellow star here in the center of the figure. And then we have the yellow concentric circles, which indicate distances of 50, 100, and 150 meters from those detectors. So within that detection area, we have 3 really quite different soil types. Right in the middle of the field, we have a silty clay loam with 19% sand and 31% clay. So this is a very heavy, very clayey, very silty soil. And then to the south and to the west, we have a silt loam, which is 25% sand and 18% clay, so a little bit more sandy. And then to the north and to the east, we have a loamy sand, which is 82% sand and only 5% clay. So especially on the north and east sides of the field here, there's a really strong soil texture gradient. To capture the influence of these changes in soil texture on the soil moisture, we conducted 4 field surveys using a HydroSense probe, which is just a TDR type probe that is inserted vertically at the surface of the soil and has prongs that are 12 centimeters long. So we conducted these field surveys on 4 different dates, shown here on the right-hand side. So you can see the HydroSense measurements at each individual point, as well as the trends over the entire field on each of these days. So in the upper left-hand corner, we have the number of measurement points, and then in the lower left-hand corner of each figure, we have the mean and mean weighted volumetric water content for each day. So what's really interesting here is that these figures really clearly show the impact of the changes in soil texture on our soil moisture measurements in each of the 4 cardinal directions during these surveys. So we used these distance-weighted volumetric water content values from each of our 4 survey dates to calibrate our neutron detectors for this location. I'm not going to show the calibration. I don't have quite enough time to do that today. But these are the points that we used to develop that calibration. Now, in comparing the neutron counts between the lithium foil and the helium-3 detectors, we see a really strong correlation. So here I'm showing the normalized neutron counts, which is calculated by dividing the corrected neutron counts. So these are neutron counts corrected for atmospheric pressure and water vapor, as well as the incoming neutron flux. So we take those corrected neutron counts divided by the N0 parameter. So this N0 parameter is derived from the calibration curves that we developed for each detector. So you can see that there's a really strong correlation here between the 2 different neutron detectors with an R-square value of 0.72. Finally, we're able to convert the neutron counts into a volumetric water content. So that's what's shown in this figure. So we have the lithium foil detectors estimated volumetric water content shown in gray, and the same for the helium-3 detector shown by the solid black line. Then we have the Teros soil moisture sensors. So these are the sensors that were installed only in the center of the field in that heavy clay soil. Those are shown by the black line. And then we have our 4 survey points indicated by the red circles. So you can see overall the 2 detectors really do a really great job of agreeing here on the volumetric water content over time. And they also, you can see, clearly respond to these precipitation events. You can see the dynamics here of the soil moisture. But really what I want to drive home here is the difference between the helium-3 and lithium foil detectors. So the mean absolute difference in volumetric water content over this entire time period was 2.3% by volume. So really, overall, there's a great agreement between this more expensive detector and another cheaper detector. Also, it's really evident from this figure, especially during the dry down periods, that the neutron detectors are able to capture the faster dry down that's occurring in those more sandy soils, while the Teros sensors show a slower dry down as a result of the heavy clay soil there in the center of the field. So these lithium foil and the helium-3 detectors both were really able to capture the influence of that soil texture and soil moisture variability in the field. So in conclusion, our lithium foil detector performed really well as compared to the commercially available alternative. Second, both neutron detectors were able to capture the influence of the variable soil texture on those field average soil moisture values. And finally, we found that these lithium foil detectors offer a really strong, in my opinion, a strong alternative to the helium-3 or even sometimes the boron trifluoride detectors. With that, I'd be happy to take any questions or comments that you have. My email is also here if you'd like to send me an email. Thank you.
Thank you, Brianna. And you are in the chat answering questions from Steve Evett about the depth. And do we have any other questions for Brianna?
I have a question. This is Andres.
Goes on, Andres.
Yeah, in figure 5, you show the dynamics, but it seems that the Teros did not respond around, April 20th or so. Yeah. And I was wondering whether that is, canopy interception captured by the detectors, or maybe I just was wondering what happened.
Yeah, I figured somebody was going to ask about that. Yes, that's exactly what happened. That particular storm was very windy, so the rain was coming in at about a 45-degree angle. So yeah, the event that Andres is talking about is about April 18th, I think.
Yeah.
Yeah, so the Teros sensors there don't respond to that event, and that's because the the helium-3 detector was basically acting as an umbrella.
Oh, okay, okay. Interesting. Okay, thank you.
Brianna, this is Mike Strobel. What's the
It is a challenge to.
I'm sorry, Mike, did I jump in on you?
No, I was just vamping. Go ahead.
Okay. Brianna, just what is the and I mean, maybe the longevity of this hasn't been out long enough, but what is the durability of these? You mentioned the two different types of sensors, and for long-term monitoring of soil moisture at a site. Obviously with like the scan sites, we have sort of a replacement schedule with sensors. And do you have any concept of that?
So the entire period that our sensors were out in the field is shown here, but I've known others, and they're in this meeting, so they can comment on this if they want to. But I've known others that have had the Hydro Innova detectors installed in a field site for several consecutive years, and as far as I know, they haven't had any issue.
Great, thank you.
The issue I have with them is lightning. It tends to fry the radio. So.
Yeah, none of these were connected, so we were collecting all this data manually.
Any more questions for Brianna? All right, we'll move on. And I should have just gone back and shared. Our next presentation is by Pedro Jimenez. And I will comment that this way, I said this was a sensors and networks session. It's sensored networks and model adjacent. So there's a little bit of a mix in the session. Sorry for some confusion there.
Hi, I'm Pedro Jimenez. I'm going to present our work entitled Using SMAP soil moisture retrievals to improve simulations of dust emissions in the southwestern US. First of all, I would like to thank my collaborators Rajesh Kumar, Jared Lee, and Senlin He. This is the motivation for the work. Dust is an abundant atmospheric aerosol, and it contributes to both the direct and indirect aerosol effects. So it has an important contribution to the Earth's radiative balance. The emissions are sensitive to the soil composition, and second to the dust mobilization that depends on wind speed, which is responsible for lifting the particles from the soil, and soil moisture that increases the cohesive forces between the soil particles. So it is harder to lift the soil in a wetter soil. Our ultimate goal with this research is to increase our fundamental understanding of the modulations that the soil moisture exerts on Earth's radiative balance through modulations of the dust emissions. And for that, we are using numerical weather prediction, and we need an accurate representation of the winds and the soil moisture. So in this presentation, I'm going to provide a summary of our analysis of the potential of using SMAP soil moisture retrievals to improve the dust simulations performed with the WorkChem model. We are using the level 2 SMAP soil moisture retrievals at 36 kilometers of grid spacing. We are only using those retrievals labeled as recommended quality. And here you can see an example of the retrievals over the contiguous US for a given day. Here on the left, you have the retrievals during the SMAP descending passes, and on the right, the ones associated with the ascending pass. So the first thing we did was to check the performance of WRF and SMAP soil moisture simulations, and for that we compare both SMAP and WRF over a multi-year period from 2015 to 2020 with ground observation from the US CRN network. So what I want to highlight here in this slide that shows the bias is that WRF has a positive bias in Western US. The simulation is too wet, and SMAP, on the contrary, seems to mitigate this bias because the bias is smaller. In Eastern US, SMAP has larger biases than WRF, you can see in this slide. If we take a look to the mean absolute error, here I show you on the left the mean absolute error from SMAP. You can see that it's lower in Western US, and this is in agreement with the bias that I showed you in the previous slide, and it's a bit larger in the East. So here on the right are the improvements of SMAP with respect to WRF, and you can see that there is added value in Western US. Not so much in the East, but over the Western US, there is a clear added value. And fortunately, this is the region with the most important dust emission sources in US. So there should be a clear added value of SMAP for dust application, or dust simulation. So to test this, we selected 6 dust episodes over the contiguous US, and we performed working simulations at 9 kilometers of grid spacing. Here you can see the characteristics of the simulations. Just highlight that we are using MERA2 as initial and boundary conditions, as well as we are doing spectral nudging to the synoptic scale. And here on the bottom are the 3 experiments that we have performed. We have run working with no soil moisture assimilation. Then a second one where we assimilate SMAP soil moisture retrievals by direct insertion into the model of the retrievals. And the third one, it is an insertion of the soil moisture in the land surface model space, which is the standard approach to assimilate soil moisture. I'm going to show you results for one case. It is the dust outbreak of March 23rd, 2017. And on the left, you can see the image from MODIS Aqua that clearly detects the dust outbreak. And on the right is here this rectangle is the location where the dust emission was important. And what we did for the evaluation was to compare the simulations against ground observations and retrievals over that region. And we use soil moisture observation from the US CRN network, aerosol optical properties from the Aeronet network, and as well as MODIS retrievals, and surface wind from the meter station over this region. In this episode, we are able to reproduce the surface winds, wind speed. Here is a slide that shows wind speed simulated and observed at 6 locations within the region from meters. And the dust episode occurs towards the end of the period where the winds are higher. At the beginning and the first part, the winds are much weaker. And you can see in this slide that WRF is able to reproduce reasonably well the magnitude of the wind speed during the dust outbreaks. So this is a case where WRF is able to reproduce the wind speed. Here I show you the soil moisture simulations for the 3 US CRN sites over the region of interest. And in black are the observations, and in blue is the default WRF simulation with no assimilation. And in these light blue dots that you see here are the retrievals from SMAP. And you can see that in this case, the direct insertion of SMAP retrievals in red is in good agreement with the observations. And is also in agreement here too, in this third case, but the default work simulation is a bit slightly better. And we also have in green the simulation in the land surface model space of the soil moisture. And in these two sites is in better agreement with the default work, and here is it's a bit worse. So one thing to highlight here is that the simulation where we simulate SMAP, the direct insertion in red, doesn't show main limitation with respect to the simulation that assimilates in the land surface model space. We are not introducing instabilities in the land surface model. Here I show you the comparison for the optical depths. On the left here is for the Aeronet site. This is one site over the region of interest. And we can see that all the simulations are in agreement with the observations of the angstrom exponent. And for the optical depth, there is also good agreement. At the beginning of the simulation period, the aerosol depth, optical depth is low, and the simulations are in agreement with that. And then you can see how the observation report an increase in the AOD, and this is captured by WorkM. And then during the main episode, there are no observations reported. But after the episode, the model is able to come back to the values registered by the Aeronet site. And this is something that we have observed at other sites during this episode. And finally, here on the right is the AOD from the MODIS retrieval as a function of the day. And you can see that it's also lower in the first part of the simulation. And then here is the dust outbreak, which is captured by WorkM. And what you can see also is that the simulation with the direct insertion of soil moisture is a bit better than the other two. And this is in agreement with the better representation of the soil moisture that we saw in the previous slide. So to conclude, SMAP soil moisture retrievals clearly show the added value with respect to worse soil moisture simulations over Western US. There is also room for improvement in the simulation, so we are thinking to combining the SMAP retrievals with ground observations to further improve the quality of the soil moisture assimilated. And we found that the direct assimilation of SMAP retrievals doesn't show any drawback in comparison with the assimilation of retrievals in the land surface model space. So we are thinking of moving ahead with this option. And after analyzing all the cases that we selected, the 6 cases, we also found that it's a bit difficult to quantify the added value of the soil moisture assimilation during the outbreaks, because first, the strong winds reduce the sensitivity of the soil moisture to the dust mobilization. And second, that the errors in the retrievals during the cases may not be representative of the long-term behavior of the errors of SMAP in this case. So to mitigate these limitations, we are planning to first analyze the impact of correcting SMAP retrievals with ground observations, and secondly, to run long continuous simulations to provide a statistically robust characterization of the added value of SMAP. Thank you, and I'll take questions now.
All right, thank you, Pedro. And Pedro is here. If we have any questions, I don't think anything in the chat yet. But do we have questions for Pedro? See, you were using CRN data as a reference. You're using the web data, or did you have access to the triplicate data?
Excuse me, Michael?
Yes. Yeah.
I think I'm not sure which one we are using. I think it's the one that measures the profile. Is available at different depths. So it's the one in the first soil layer.
Yeah, so it's emerged. It's the merged or quality controlled value.
We did use also the during the beginning of in the first year, there was available one that is instantaneous, right?
Mhm.
So we use that one, and then there is this second one that is an average, hourly average, and we compare them. We compare them the two, and we didn't see a large difference between the two during the overlapping period.
Any other questions? So if we don't,
Sorry, just
go ahead, Tyson.
a quick question. Really interesting and something different than we often, hear at these meetings. I'm just a little curious about, what kind of monitoring sites exist that would provide data both on the soil moisture conditions as well as the dust emission. Is there a good set of dust emission monitoring sites scattered across the U.S., or I just wonder what kind of data is available in that regards.
There's not much available. That's why in the comparison we focus on optical depth, which is the data that is widely available. But to my knowledge, there's not much available in terms of dust emissions.
Dust emissions, if you look at the aerosols in the atmosphere and particulates in the atmosphere, maybe the Aura or Calypso satellites might do that. The National Atmospheric Deposition Program has wind erosion deposition data that it's not right where you are, but it may give you, I don't know much about that data set, but it's collections across the US for landfall of dust may be of use. I can see if I can shoot you a name or two related to that. We'll put it in the chat so other people can see it. I don't know that much about it, so.
Okay, I'll take a look to this data set.
And Mike Pilecki posted a link to a paper. In the Southwest, there's a paper looking at coccidioidomycosis, and its recurrence in relation to dust and soil moisture. So the dust, the idea behind it is cocci is spread by a fungus, and the fungus is airborne in a dust form after it is it spreads and then dries. So there's a seasonality and a cycling to it that has to do with a large moist condition that spreads the fungus, and then a dry condition that kills it, and then the wind picks up and carries it. So human health certainly is a use for, has a place in soil moisture in the dust atmospheres. That was a horrible pun, but air quality and human health are all related together there. So that might be another avenue to look at the NIH air quality standards to help you understand the dust. Certainly with wildfires right now, it's not necessarily dust, but smoke and haze are issues that would carry through on some of this. We are getting close to the end of this section, so I wanted to do one quick poll to ask another question regarding conferences. So here we are in a virtual conference, but in the future, do you see your conference workshops? Let's pretend that everybody becomes immune to COVID and all its variants. How do you see your conference attendance changing in the future? And this is going to help us design our courses in time, whether we stay virtual, hybrid, in person, and how we kind of balance that. So take some time. You have 5 minutes or so. We'll return in 5 for our last session of the day. That would be 4 p.m. Eastern Daylight. So enjoy your bio break while we, and think about your own conference attendance in the near future and what you're considering. See you in a few.